In today's lesson, we're going to take a look at algebraic structures in the context of what are called groups. An algebraic structure is a set and either one or more binary operations that behave in certain ways. You should be getting pretty familiar with these rules by now. First, there's closure within the binary operation and the set. The operation must be associative. There must be an identity element. Every element must have an inverse. And then also, optionally, the operation can be commutative. An algebraic structure defines the relationship between the elements of a set and a binary operation. You don't need numbers, you just need certain structural relationships. Let's check this Cayley table for the algebraic rules. First of all, we can see that this has closure because there aren't any elements in the center of the Cayley table that aren't also on the edges. Next, we're going to check to see if there's an identity element. Luckily, there's an easy way to do this. All we have to do is look at that leftmost column, the one with all of our elements, and see if that column gets repeated exactly anywhere in the table. And we see that it does, underneath the red circle. This means that red circle is our identity element because it doesn't affect the element when the element gets starred with red circle. Once we know that red circle is the identity element, it becomes very easy to check to make sure that every element has an inverse. All we have to do is make sure that there is a red circle in each column. And we can see that there is. It's in row 1 in the first column, row 3 in the second column, etc. Testing for associativity would be tedious. Let's test this triplet for associativity. First, we're going to take the red circle and star it with the purple square. And that gives us a purple square. Then we take the result of that and star that with the green square. And that gives us a yellow circle. So we keep that yellow circle in mind, and now this time we're going to try it again, except this time we're going to start by starring the purple square and the green square. And when we do that, we get the yellow circle. Now we have to take the yellow circle and start with the red circle, and when we do that, we get the yellow circle. So that means in this particular situation, it did not matter whether we did the first pair first or the second pair first. In order to test the entire structure for associativity, we could go through and test every possible combination of 3 elements to see if this property holds. Fortunately, there are other mathematical ways to test for associativity, but those ways are beyond the scope of this lesson. Luckily, we don't have to do any of that because we happen to know that this structure is associative. Other mathematicians have already checked for us. If this structure is commutative, then we should see symmetry across the top left to bottom right diagonal. This particular table does not look symmetric, although it comes very close. But in particular, if you look at the very bottom right, at the 2x2 square in the bottom right corner, it's not symmetric along this diagonal. This is because purple square star blue square gives us orange circle. Whereas if you reverse the inputs and do blue square star purple square, you get yellow circle. The only thing that failed here is commutativity, and commutativity is optional. And that means that this binary operation with this set passes the requirements and is therefore an algebraic structure. Now that we understand what algebraic structure means, let's examine some of our familiar binary operations and number sets. How about integers and addition? Do the integers and addition have closure? Yes, because it is impossible to add 2 integers together and get an answer that is something other than an integer. How about an identity element? Well, with integers and addition, 0 is the identity element. You can add 0 to anything, and you'll get that same thing out. How about the associative property? Well, it is true that integers and addition are associative. But associativity is where subtraction falls apart, because subtraction is not associative. Does every integer have an inverse? Yes, it does. For every number, there is another number that you can add to it to get 0. And then there's the optional property, the commutativity. Addition does happen to be commutative. However, subtraction is not commutative. And this is another way in which subtraction differs from addition. How about another possibly algebraic structure, integers and division? Well, first we check out to see if it has closure, and we notice immediately that it does not. Just because you're going to divide one integer by another integer, that does not necessarily mean you will get an integer. Since integers and division falls apart immediately on the very first principle, we don't even have to check the rest. We already know that integers and division together are not an algebraic structure. What about the set of rational numbers and the binary operation of multiplication? Do these hold? Convince yourself. These do hold. This is an algebraic structure. We use the properties of algebraic structures to solve equations. Addition and multiplication, together with the real numbers, which are probably all of the numbers that you know, create an algebraic structure. We should only use addition and multiplication in algebra because subtraction and division are not algebraic operations.